So good afternoon to everybody and welcome to the Lectio Magistralis for the International Prize TULLIO Levi Civita. As many of you know, last week the Pope visited Sapienza, and thanks to my little son Cosimo, I was honored to welcome him in the brief encounter with the kids of Sapienza's kindergarten. This week, I'm even more honored to welcome and introduce Herbert Spohn, Emeritus Professor of Excellence at the Technical University of Munich, and to say a few words about some of the several important achievements he obtained during his scientific life. Herbert studied physics at University of Stuttgart, Oregon State University, and Ludwig Maximilian University of Munich, from which he received his PhD in 1975. He was a postdoc at Yeshua University, at Rutgers University in the group of Joel Lebowitz, at Princeton University in the group of Elliot Lieb, and at KU Leuven in the group of André Verboer. After a DFK Heisenberg Fellowship from 1980 to 1982, he became Professor of Condensed Matter Physics at Ludwig Maximilian University. And in 1998, he moved to Technical University of Munich as professors of mathematical physics. Still, I remember the plate on the corridor. Yes. Lehrstuhl für mathematische Physik und angewandte Wahrscheinlichkeitstheorie. Quite a long name. As mentioned. More recently, he received honorary doctorates from Université Paris-Dauphine and Université Paris-Diderot. As far as scientific interests are concerned, the broader research field of Herbert Spohn is non-equilibrium statistical mechanics, and he contributed to the theory of kinetic limits, in particular to the derivation of the Boltzmann equation for our sphere, and to the validity of the kinetic equation for weakly nonlinear wave equations with random initial conditions. In the 80s, he pioneered the hydrodynamic limit for stochastic manic particle systems, which is still an active area of research in probability theory. A somewhat different direction is the motion of interfaces. A highly influential result is the first derivation of motion by mean curvature from the stochastic Ginzburg-Landau equation. This research naturally paved the way to the dynamics of growing surfaces, which on large scales are governed by the Cardan-Parisi-Zhang equation. Herbert obtained the exact formula for the universal two-point scaling function. His early contributions led to vast efforts and formed a novel mathematical area known as integrable probability. Herbert also pioneered the research in the quantum theory of open systems and in the development of adiabatic theory for quantum systems near to equilibrium with slowly varying external perturbations. In the recent years, his focus is on the generalized hydrodynamics of integrable classical many-particle systems. And with respect to this recent interest, I have been very impressed how you, Herbert, you could start a completely new research line after retirement. So this is a message of hope for all of us who are worried about life after retirement. Still, you can do a full theory after that. So Herbert is author of 3 books: Large-Scale Dynamics of Interantic Particles, which is known to most of the audience, Dynamics of Charged Particles and the Radiation Field in 2004, and Hydrodynamic Scales of Integrable Many-Particle Systems is the most recent one in 2024. The research work of Professor Spohn has been recognized by high distinctions, including the following. In 1993, the Max Planck Research Award, jointly with Joel Lebowitz. 2011 was the Annus Mirabilis of Herbert. He got 3 prizes. The Leonard Heisenberg Prize for Mathematics and Physics by the American Mathematical Society, the Danny Heinemann Prize for Mathematical Physics by the American Institute of Physics and the American Physical Society, Here in Rome, the Premio Caterina Tommasoni and Felice Pietro Pisesi by the Department of Physics of Sapienza. In 2014, he got the George Cantor Medaille from the German Mathematical Association. And in 2015, the Ore.Prize, which is the highest recognition awarded by the International Association of Mathematical Physics. In 2017, the Max Planck Medal by the German Physical Society. And in 2019, the prestigious Boltzmann Medal by the UPAP Commission about Statistical Physics. To put the prizes in perspective, let me add that Herbert is the only person ever who got both the Cantor Medal, which is the highest recognition of the German mathematical community, and the Max Planck Medal, which is the highest recognition of the German physical community. So the highest distinction in both mathematics and physics. Now I proceed to read the motivation of the prize for the quality, the depth, the innovative character, and the international value of over 50 years of activity. The Scientific Committee of the Levi Civita Prize in Mechanical and Mathematical Sciences is honored to propose Herbert Spohn as the recipients of the 2025 prize edition.
Thank you very much. Very kind introduction. I really, we have to open it. Okay. We need a picture also.
Yeah, I need a picture.
Wow.
You know, this has been designed by one of the recipients of the prize, Professor Carfor, together with the medal.
Okay.
You know, in these times of war, silver is becoming precious. Be careful. Thanks a
Very
lot.
much. Well, thank you very much.
Chi fa la foto?
I have two words about Herbert, about my experience. Just since this has
Come here.
this is not mentioned neither by Gianluca nor motivation. I would say just two words about my experience. I think the first conference I ever went, Herbert was in the audience. He was very friendly. After my talk, which was short and basically nonsense, he came to me and said, "Yeah, what you're doing is interesting." I couldn't believe this, but you should pursue this direction. And okay, I took that quite seriously, of course, coming from Herbert, and this helped a lot. And all of this happened not just at the first conference, but every time I met Herbert, he was always very friendly to me, always encouraging some direction, and always helping. So I think he has really a great impact, not only on me, but on a lot of people, young research, and they really recognize this. And this is special thanks to Herbert.
Okay. Thank you very much. So, should I continue with the talk?
Please.
Okay. So, I mean, first, thank you very much. I mean, it's absolute surprise and a great honor. I'm sort of really pleased and thank the Commission for doing all the work. Also, Gianluca, I mean, he had to sort of prepare this presentation, and thank you. I mean, so okay. So, as I guess Gianluca mentioned, the kind of things which I've been doing the recent years is actually, well, I put here a title which I hope you like. I mean, I call it Integrable Fluids, Statics and Dynamics. Okay, and so I realized that, you know, I mean, maybe with few exceptions, I mean, there's not so much background, so I will give you a little bit more background of what's actually going to happen. But in case, I mean, somebody should be interested, I mean, as Gianluca mentioned, I mean, there is a book which I've written, which is the Hydrodynamic Scales of Integrable Many-Body Systems, which is real scientific, and, you know, if you really are interested, I mean, you can read more Okay, so let me start with maybe there's a pointer. There's also a timer. Okay. All right. So let me first. So I want to do integrable fluids now. Integrability is a very fine-tuned property, and so from moment one, I have to restrict myself to spatial one. Right? I mean, in higher dimensions, 2 or 3. I mean, this integrability presumably doesn't exist, or maybe in some very exotic situations. So let me just sort of look. Remember that my particles are sort of always in one dimension. And in this slide, I sort of would like to sort of explain you a little bit of the much more common case, namely, the case of non-integrable systems. Okay. And so here I've written down, the formula which everybody knows. So I have classical particles that are living on the line, and there's some, let's say, repulsive interaction potential. Otherwise, you might form bound states and things like that, which might be sort of more complicated anyway. So I'm looking at this type of non-integrable systems. And one way to detect the non-integrability is actually to look at the scattering experiment. So you imagine that, at sort of very early times, I mean, you have particles coming in very far apart with specific velocities. Then there will be a lot of interactions. I mean, they're moving around. The number is sort of, at that point, sort of fairly arbitrary. And then as you wait long enough, I mean, then, you get the outgoing velocities and so momenta, and then you can sort of think about this map from incoming to outgoing momenta. And this map will be chaotic. I mean, chaotic means that, whenever I make a small change in my initial setup, you will see something totally different. And you see that the only conservation laws which you can impose is sort of, this kind of conservation laws. I mean, if I put n equal to 1, then you have conservation of momentum, and if I take n equal to 2, you have conservation of energy, because, far away, I mean, this potential has decayed to 0, and it's only kinetic energy is left over. Okay. Now, that's fine, but you can sort of now do sort of, let's say, more concretely. I mean, that's sort of, since I put sort of hydrodynamics in my title. I mean, you can sort of see, even in one dimension, you can sort of look at the hydrodynamics of the system. And for the hydrodynamics, the key quantities are the locally conserved quantities. In this case, you have the number of particles. I mean, you have the total momentum. I put here momentum, and P appears later on as pressure, but I mean, here it's the momentum, and then I have the energy. And the claim is that there are no further conserved fields. That's actually, in that context, never proved. I think it's a beautiful problem, but maybe also difficult. But there are results when you look at the same problem for quantum spin chains. When you look at quantum spin chains, there is sort of a theorem which tells you that you have either the trivial conserved quantities like energy, and then depending on the model, maybe spin or so, and infinitely many. There's nothing in between. It's a complete dichotomy. Okay, so now we are in this non-integrable case. So the way you do hydrodynamics is that we know what the equilibrium measure is. You just put local equilibrium. So you have a slow variation of initial data, and because we do statistical mechanics and local equilibrium is a statistical property, we actually have random initial data. See, the dynamics is deterministic, but the initial data are random, and they have to be random. If I make them non-random, then there are all kinds of other things appearing which are difficult to describe. But even the Euler equations sort of look quite simple. I mean, they rely on the fact that your initial data have a random distribution. In this case, I mean, locally, just the usual Gibbs distribution. Okay, and then of course, once you assume this, and then you wave your hands a little bit, I mean, then you get this as Euler equation. So you see that you have 3 fields. And it's just sort of a local conservation law, and you see that the currents have to be functions of the 3 densities, and this is a purely static computation, right? I mean, so you have a microscopic definition of what is a current, because you know what the conservation laws are, and then you have to take sort of expectation of that quantity, and this fixes this particular function. Okay. All right, so that's quite simple. So we of course sort of much used. I just want to point out. I mean, I put here the atomic class. I mean, you might wonder, are this equation used at all? Yes, I mean, so when you go back to the first atomic bomb, and they sort of put a lot of energy, in a very small region. And well, I mean, they wanted to sort of know how the energy is sort of propagating, and well, I mean, it's essentially a planar problem, but on top of this, I mean, you have rotational sort of invariance, and therefore it's essentially a one-dimensional problem. So when you look at the old papers of Fermi and Bethe, at Los Alamos, I mean, they were sort of estimating using such type of equations in order to find out. And I mean, what I find really truly amazing, of course, this is sort of, this was not a high precision experiment, right? I mean, they just wanted to know roughly, how long they had to wait until sort of, the energy was passing by. But nowadays you can make sort of numerical simulations, and I still find it sort of really interesting to see how these particles, which sort of locally look very random, how they actually manage to reproduce these equations with absolute precision. I mean, it's really, I mean, I have seen many pictures, but I still find this sort of very, very sort of surprising and interesting. Okay, so now comes sort of the real thing. Namely, now I want to go to the integrable case. And now you have to fine tune. Okay, so this is something you have to get used to. You see, I mean, in many things in mathematical physics, you sort of, maybe you have sort of approximate quantities, and then it's sort of, if certain conditions are satisfied, I mean, then you couldn't prove something here. You have to, from the outset, you have to sort of do something sort of very drastic. So I want to do an integrable case. And the only one which is actually known, and presumably this is the only one, is the model which Titolo discovered, which is the 1/c² interaction potential. So it's, sort of decays exponentially and has a sharp peak at the origin. So actually the order of particles is preserved. So if I start with initial order, I mean, then it will not change because, I mean, they cannot pass through each other, right? Okay, and now for the Titolo model, you can sort of ask yourself again about this asymptotic velocities. I mean, you do the scattering experiment. In this case, there is actually proof, but I don't want to go into that. The main point is that what you find is that now, this map from incoming to outgoing is actually quite simple. It just reverses the order of the momenta. So it's as simple as the map could be. But as soon as I go away from the 1/c², I mean, then things sort of seem to become chaotic. Okay. Now, what I do want to do in this talk is that I sort of want to focus on a very concrete problem, which actually is sort of an approximation, or can be viewed as an approximation to the Titolo fluid. Namely, you say, okay, particles are mostly ordered, and then maybe it suffices to sort of approximate this 1/c² by the exponential at the price that you put in the exponential sort of the stretches. I mean, the position as labeled. I mean, so it's no longer like the usual systems where you can relabel the particles, relabel the particles. I mean, here the particles from the outset are labeled, and it's the interaction in terms of nearest neighbors of that labeling. Okay. Now, I mean, you look at this thing. Here we had the order is preserved. Here there's no order. I mean, so the QJ can be anything. I mean, so initially they are whatever they are, and there's no specific order. I mean, so I mean, this is important because it is very different from what Titolo. So in that regime, I mean, the total fluid is no longer a good approximation to the Titolo. Okay, and now you can ask, what is the next order? To this thing. I mean, what is the next order convection? And this is something which is called the Herbert shifter. And I mentioned it already here because it will be a quantity which reappears over and over. I mean, so when you think about this scattering, then on the top, I mean, this is the true asymptotic behavior, but you know, this is sort of, you know, the linear in time behavior. But then you have order one corrections to this behavior, and in the case of the Toda lattice, it's given by this particular quantity. Anyway, you will see a little bit more of that. And of course, for finite volume, you can just put it on a ring, and you can also study the Toda lattice on a ring. Okay, so now let me see what I want you to do next. Now I have to push here. Ah, yeah, okay, so since this is supposed to be, you know, a little bit of introduction, I mean, so let me give you sort of a few other integrable fluids. One of them is the coordinated freeze equation, which is a PDE, nonlinear wave equation, which has the same property. I mean, it has many conserved quantities. I mean, there is something called the Box-Ball system. This is sort of the space-time discrete model. So, you know, Box-Ball just means that, you know, you have sort of sides on the one-dimensional lattice which are either empty or occupied. I mean, the ball is occupied and the box is empty. And now you give a deterministic map which goes from from time 0 to time 1, and then you just keep going. And this the reason I mentioned this, I mean, this is sort of one of the, I mean, sort of mathematical model which you can actually analyze in considerable detail. I mean, the other models which I mentioned over here, I mean, you know much less. But so let me just sort of explain this in one word, so you can sort of attach sort of something with the box ball. I mean, so the point is that you scan the configuration from left to the right, and the rule is that each particles can jump exactly once. I mean, so you know, if I take this one and jump it forward, then I mark it, and when I come to the update, then I simply ignore that particle. So that's rule one, exactly one jump. Okay. Now, how far do you jump is the following rule. I mean, you take the closest right empty side. So this one will jump over here, okay, and then the next one will jump over here, etc. And if you do this thing, I mean, you will get integration. I'm not going to go into this. I'm just going to tell you, you know, that there's a wide variety of models which sort of, at first sight, sort of look extremely different. But when you go to the hydrodynamic scale, you know, they have a lot of similarity. Okay, so the next thing is the nonlinear Schrödinger equation in one dimension. That's also an integrable system. You can sort of do a discretization of this equation, and that's called the Abel-Lattice. I mean, so you replace the continuum here by the discrete lattice, and you somehow make the right approximation to this nonlinear thing. I mean, you know, you can sort of do various, but it's only this very particular choice which makes it an integrable system. There's, you know, very famously the linear model. I mean, these are quantum mechanical particles which are interacting in one dimension through a delta function potential, and there you can do big ansatz and other kind of things. Okay. Now, the common feature of all these models is that you have n. I mean, you know, n is, you know, I mean, here of course for the KDV, I mean, you know, there's no n really. I mean, you have sort of immediately the infinite power of local conservation laws. Maybe here, if you confine this, well, I don't know, yeah, maybe for this model, if you confine to a finite lattice, then you have exactly n anyway. I mean, so you have an extensive number of local conservation laws. I mean, that's the definition. That's my definition of integrability. Of course, you know, there's classical mechanics and what you learn now, your lecture course on integrable systems. This maybe can be done, but it's actually not very useful in our context. I mean, the real point are the local conservation laws, and sort of, you know, when I think about integrable fluids, you know, I mean that I have a system which have this kind of, you know, many extensive conservation laws. And of course, the main point of this conservation law, so here is sort of like a microscopic conservation law. So you see, this is an operator, maybe a complicated function on phase space, but never, you know, it's indexed by x and t, by space and time. And but you have sort of, you know, this type of continuum equation. So here's the ddt, here ddx, and so that tells you, in some sense, you know, that this quantity can be changed only through sort of motion through the boundary. But you know, this is a very, I mean, you cannot use anything with this kind of equation. I mean, you have to manipulate it in such a way that you can get interesting information. But you know, it's this really the starting point of having an integrable fluid. And what I want to do now is sort of, I mean, you can ask me questions any moment you want to, right? I mean, so I'm just sort of going here through my slide, but maybe things are not so clear on it, and just ask some questions. So what I want, the plan is the following. I mean, I want to sort of just continue with the total fluid, simply because that's the model which we understand best, and you know, you don't have to think about many models at the same time, and so you can sort of concentrate on this one single model, which I will talk about all the way up to the end. And for this model, I want to sort of give you some flavor of what I mean by statics and what I mean by dynamics. Okay? So this is, I don't know how somebody is keeping my time, or when did we start?
You're free, more or less.
No, but I don't know. I have here my watch, but I didn't know when I started actually. Anyway, okay. So you will stop me. Okay. I didn't prepare many things. I mean, so you know, we're not really in a hurry. Okay. So let me explain you a little bit the toda. So here I've written down again. I mean, you know, this equations of motion. I mean, here you see this exponential interaction. It depends on the difference. So there's sort of momentum conservation, and here I've written, you know, what I mean by open. I mean, these particles are just sort of living on the real line. And okay, then we have an important quantity, which is the free volume, and you know, the difference between Qj plus 1 and Qj. This stretch, I mean, this will come up all over. So just a short notation, okay? Now, looking at this model, of course, you don't know what to do, but you know, if you would have lived at the Courant Institute in the early 70s, people, you know, the famous people would have told you what to do. I mean, you have to look for a Lax matrix. And, you know, people were doing more continuum equations, but Blaschka was sort of the happy person to understand, and he said, okay, why don't I find a Lax matrix for the total lattice, okay? And so the way how it goes is that he first introduced something which are now called the Blaschka variables. So this is just the exponential of this stretch. And you know, at the moment I am thinking of my labels going from 1 up to n, so I'm looking sort of at a finite system. And then you rewrite the equations of motion in terms of these A variables. And now you see they look already very different because you know, I only have sort of quadratic nonlinearities, right? I mean, so before it was maybe more if you write down Newton's, you know, so Newton's equation of motion. Anyway, so here it looks sort of simple, and then you can sort of put the boundary conditions, you know, the way you would think. I mean, and now you think sort of a little bit more like a lattice system, right, rather than particles moving on the line. But of course, once I know something about this, then you can go back to more sort of to the particle picture. So there's the same thing. Okay, so you know, can you do the closing? I mean, it's just a usual periodic boundary condition, or the open is that you know, you just do, I mean, the P1 up to n, and then there are only n minus 1 stretches, and so then you put it just like this. Okay. All right, so I mean, this is fine. I mean, you first introduce the variables, but now comes the Lax matrix, and the Lax matrix is just a Jacobi matrix. It's something very simple, right? I mean, so you put the P1 up to Pj, and all the momenta on the diagonal, and then there are two off diagonals. It's a symmetric matrix, and you just put the A's along the off diagonal, and that's it. So that's a Jacobi matrix. Okay. So here it's written in formulas, and then okay, by itself that doesn't help so much. I mean, so that's fine. I mean, I put here because you know, when you change boundary conditions, you might lose integrability, but the open and the closed are both integrable. You know, I mean, it's just differ that you know, this matrix element for the open one is 0 and for the closed one is A. Okay, but now the real point of the story is that there's a companion matrix, so it's a pair. I mean, that's the next pair. And the companion matrix is sort of now an anti-Hermitian matrix. It has minus A and 0 on the diagonal, minus A on the upper one, and A on the lower one, and this one depending on the case. And so this one would generate unitary. Okay. Now, you see, these are all time-dependent matrices because I'm plugging into a solution of this system, right? Of the dynamics of the total fluid. And now the magic, and without this, I mean, we couldn't do anything. Is that when I take the time derivative of L, it's just the commutator of B and L. And so this sort of makes the life, if you want so. Now, of course, this is just the introduction, right? And now you have to come more. But I just want to say that unless you have sort of something comparable, I mean, it's not always sort of exactly this type of Lax matrix. There are other kind of integrabilities which you sort of know somewhat different properties. But anyway, something of that sort you have to know. Otherwise, I mean, you have to. You cannot simply continue. Okay, so now you have this nice Lax matrix, so you can look at the eigenvalues. I mean, this is the eigenvalue problem. And because of this commutation relation, when you look at the exponential of B of t, you see that this is an isospectral map, and therefore, the eigenvalues themselves are not changing in time. So by this simple trick, I have found my n conservation laws, right? I mean, I just have to look at these are complicated functions of my A's and my P's, but nevertheless, I mean, they're mathematically sort of, sort of given in a very concrete way, and therefore, they are sort of conserved. But there's a companion paper by Hani who sort of figured out something a little bit similar, and he noted already. I mean, he never had the Lax matrix, but had some other scheme. These quantities are not very good quantities because they are non-local. The eigenvalue, if I change something else, I mean, somehow it depends on everything, right? But now it's very easy to go from these non-local ones to local ones because I can take any functions of the lambdas. And then the simple observation is that the good conservation loss is simply the trace of L to the power n. And then you see it's a good quantity because if I write out the trace, then you see that the density. This is an extensive quantity. The density is simply, the nth power of this matrix, but the nth power is something which is still sort of, a matrix which has a finite band. I mean, so this is a strictly local quantity, and I still have to add the stretch to this conservation laws, but now I have the family conservation laws of strictly local conservation laws. Okay, so this is a very, very brief summary of the background, and now I want to do the statics. Okay, so forget about the dynamics. I want to do the statics. Okay, so how do we do statics? Well, you have the Hamiltonian e to the minus beta h. This is your Gibbs distribution. Okay. Now I have many conservation laws. Well, you look up Gibbs. I mean, he also had already cases where he had sort of several conservation laws. And he told you what to do. I mean, you just take the linear combination of these conservation laws and put it in the exponential. Okay. So let me follow Gibbs and let me just do that. And now, of course, now you see. Okay. So first of all, there's a little my volume element. That's the TPQ. I mean, this becomes sort of this one. Okay. So that's no big deal. But here is sort of this sum, right? I mean, so here you have the zero. I mean, this is the stretch. I mean, sort of like the density, and then you have many more. I mean, and each one of them has a chemical potential. This is the way how you find it in physics text. Even nowadays, everywhere, this formula appears whenever you see a paper on generalized hydrodynamics. I mean, they have this formula. I never liked this formula because it sort of goes mathematics sort of like 100 or even more years back. I mean, functions are defined by power series. I mean, it's just sort of not really the necessarily good perspective. So now you do your little algebra. I mean, of course, you can think of this as given by power series, but now you can take it simply a general, let's say, continuous function, and you take the trace of v to the L, right? I mean, so this is just simple algebra, and now you see that you get a nice and compact formula. So here's sort of the a priori, and then of course there's sort of the Boltzmann weight, and it's a trace of some function. And when you look at it, I mean, you know, you want to have this integrable, so you want to have that this function maybe sort of increases linearly at infinity. Otherwise, you know, you get difficulty of normalizing, and this is sort of the generic version of the Gibbs measure for an integrable system. Now we have thermodynamics, which has the parameter P. I mean, this is the pressure now, which is a dual to the stretches, and then you have a full function, which has to be like this because, you know, I have an infinite number of conservation laws, right? So now you have thermodynamics, which has sort of these two parameters. Okay, now I'll let you sort of contemplate about this thing, and then, you know, I mean, years back when I first looked at this, you know, I said, yeah, I have a very nice formula, but you know, can I say anything? I mean, it looks like not such a simple problem, right? I mean, thermal equilibrium is still easy. You see, thermal equilibrium, you know, this is a quadratic function. So then you have base to the power L squared. And then you see that, you know, then the momenta are Maxwellian distributed and the A's are high distributed, you see, because I mean, you get from this sort of A times E to the A squared, actually, minus A squared. Okay, so in thermal equilibrium, I still have independence, okay? But if I don't, but I don't want to have thermal equilibrium necessarily, and then I get some complicated thing which I don't know what to do with, okay? Okay, so but before doing this, I mean, let's ask, you know, well, I mean, I can write down these Gibbs, but, you know, let's ask the question. Okay, now what is the question? The question is, you know, I'm looking now at the conserved quantity. So here are my alphas, and you see now the Lex matrix, the entries of the Lex matrix are equipped with this measure. So now it's a random matrix. It's a random Jacobi matrix. And now if you look any book on random matrices, I mean, the first thing what you want to know, what is the density of states, right? I mean, so here I've written down the density of states, so you put a little delta, you know, wherever I have this eigenvalue, and then, you know, what you sort of generically suspect in this one-dimensional situation and with a lot of randomness, this quantity will have a non-random limit. Okay? And this is sort of what you want to have, because you see, I mean, this is what I put here as the Lex microscope. The Lex microscope is saying the following: I look at a little piece of the fluid, and now I just look at the configuration in that little piece. Right? And now I'm asking myself, what are the conserved quantities? It's sort of like looking for fluid, you know, what is the energy and the momentum in this little fluid piece. But now, of course, I have to use the Lex matrix. So you know, the Lex matrix, if I feed this microscopic configuration into the Lex matrix, just of the number of particles which are in this little region, then it gives me the values of the conserved quantities. Okay, and so the density of states will be something which is slowly varying. So you know, if I wait a little bit, you know, of course, I will get a lot of rearrangement of particles. I mean, they are not close, but the density of state is changing slowly. And also, if I'm going, you know, nearby, I mean, you know, sort of here's my fluid cell, and I look at the neighboring fluid cell again. I mean, you know, initially I put sort of an initial state which has slow variation, and therefore, you know, we'll have slow. You're laughing. I mean, this is something which I've been telling you for many times on different occasions. But you know, this kind of sort of, you know, philosophy sort of, you know, is perfectly for this case also, right? I mean, it's not a semi-classical limit, but it's still sort of the same one. Okay, so you see that these somewhat fictitious equations, which I have never written down and presumably will actually never write down, that the hydrodynamic equations is actually an evolution equation for the local density of states. And of course, it's always a function, right? And so on. Okay, now let me see what I can do next. Okay, now comes the surprise. At least to me, I mean, you know, I mean, it looks rather complicated, but nevertheless, what you end up with is that you can prove that, you know, when I take this limit, there is actually a free energy functional, and its minimizer is the density of states. And you see, this is, I mean, so okay, maybe we first look at this free energy function. So rho is here just a density, right? I mean, it's positive and normalized to 1, and this is rho. I mean, so various terms. I mean, this is obviously this sort of like the potential energy, the confining potential. Here you see the rho log rho. I mean, that's the entropy term. But then I get this term, which is specific for Toda, which is the log of this particular combination. Okay, and so this is the correct free energy function. No, it's sort of it's the correct free. I mean, actually, it's a large deviation function for this problem. And the main point is that you know one thing which I can do is that if I minimize, if I have the minimizer, then actually I have obtained you know the density of states. It's a unique minimizer of this function. And this is very surprising because you see, I mean, even if it's a random, let's say a random Jacobi matrix, you ask what is the density of states. I mean, there is no formula. You know, people prove maybe you know density of states is some smooth function, or maybe it has some. Anyway, I mean, you know, they prove maybe certain properties, but the fact that you can such an explicit expression is sort of extremely surprising. Now you say, what is explicit? It's a complicated functional. But you see, it's not so complicated. I mean, it's just a function of a single variable, and we have computers, and you know, we can do computers and do more clever things, and so I will show you later on. I mean, some pictures. I mean, you should think of this sort of like you know a very explicit formula, which is, you know, it's not doing Monte Carlo and then trying to sort of okay. Anyway, so let's see. Yeah, here I put this TBA formalism because you see, I mean, it's a minimizer, so there will be all Lagrange equations, and you can do a lot of identities, and I mean, this is what in the jargon is called TBA formalism. It's not to be announced, but it's thermodynamic beta ansatz. Okay. Okay, and so here I put it's the generic structure of integrable fluids. I mean, you know, in all of these models which I showed you, I mean, there will be some analog. Okay, so now you have to ask a question. If nobody asks a question.
Is this free energy coming as Legendre transform or something? What? Is this a Legendre free energy function coming as the Legendre transform of the function?
No, it's not. Well, no. Well, it's a little bit more complicated. Yeah, no, not. Yeah, no. If you just stare at this formula, yeah, no, that's more complicated because then it would soon be in a much larger space, right? You see, the point is that of course you can have the understood functions of very large spaces. I mean, here it's sort of in a very small space, so to speak. So, but nobody asked the question. No, okay. So I asked the question. I mean, so this is the log, right? So what do you do if this expression happens to be negative? Okay, so the correct statement is that whenever this quantity happens to be negative, then the free energy is infinity. Okay? And then you have to prove a little bit, you know, that for the minimizer, actually, this is actually a positive quantity. So somehow, you know, the infinity is far away from what you actually want to solve. And surprisingly, well, okay. When you look in random matrix theory, you know, they use a different notation, but this is actually the Zaher's relation for random matrices. So anybody who knows the Zaher's relation, I mean, it's just a version of the Zaher's relation. Anyway, so okay, now comes the second part. I mean, so now I want to tell you a little bit about that dynamics, which is much more qualitative. I mean, there are actually proofs, but I mean, I'm certainly not going into them. And I want to, you see, I put here, I want to talk about, I mean, the aspects of the dynamics which I want to discuss with you is what in the physics literature is called quasiparticles. I mean, you know, the literature is full of quasiparticles, and when you ask physicists what is really the quasiparticle, I mean, then they start sort of waving their hands. I mean, this is sort of not very clear. But here I want to sort of give you a much more mathematical and clear definition. Okay, so here what you see here is forgot already. I guess maybe 16 Toda particles, and time is here. And we just solve the equations of motion, right? And the blue lines are the actual trajectories of the particles. And so you see that you know, sometimes they overlap here a little bit for that particular density, right? I mean, here they overlap quite a bit. Anyway, so this is the motion of particles, and of course I can look at one specific particle, sort of, you know, a tag particle if you want. So that's this violet line here, or magnetar. I mean, anyway, so that's this line. Okay, now the quasi-particle is an object which is supposed to maintain its velocity as good as possible. Okay, so here by my hand I put in here the quasi-particle. So here you see it coming in with this velocity. This looks almost the same. This looks almost the same. Here I was not completely sure. I might have put this one anyway. So I just draw this by hand, and now you see that there's sort of a quasi-particle which has a very different type of motion. You see, it's basically following for a while its initial velocity, but then, you know, it sort of jumps to the right and jumps to the left, and then there's some blurry region where we don't know where it is. Okay? Now, with this picture, which I like, I put it in my book. But you cannot do any mathematics. I mean, it's a sort of more an illustration of you know, what these things look like. And so I have sort of, you know, Alberto Brolo, I mean, who knows how to work with computers. So we said, okay, that's a nice picture what you have. I mean, why don't you take more particles? Okay, now come more particles. Okay, now you see this. Okay, so where are your quasi-particles? Okay. Well, you know, it looks a little bit like before, but yeah, I mean, you see, I mean, now he has 200 particles, and so of course things are correct. Yes, okay. And so now comes sort of this beautiful idea which came up. I mean, that there is a mathematical definition of quasi-particles. Okay. And so I just want to repeat. I mean, that you can follow. So here I put the hard parts. I mean, so here you have this perfect, you know, just particles on the line which are hard waters that then do elastic reflections, and you see that the quasi-particle would come here and then it jumps by A and then it continues here, and this quasi-particle would come here, jumps here like this. Okay, so here you can follow, and you see that for the hard watts, I mean, the quasi-particles are perfectly defined, and anybody who ever looked at this system, of course, studied the quasi-particles, because it's a thing which you can analyze easily and which has the nice property that when you let A swing to 0, then these are just free particles. Okay? So, you know, I mean, Joel has papers on this, I mean, you know, many years back, and of course, he looked, they called it pulses at that time, but because the term quasi-particle was not yet okay, so that's fine. And now you see the Toda has a problem that you know, here I don't really actually know. I mean, of course, here and here, you know, if I wait, I mean, this is one and this is one. That's quite clear. But here in the middle, I don't know. So it's really blurred, and so you don't really know what the quasi-particle is. And now comes sort of this nice observation that so first of all, I want to give a tag to the quasi-particle. Well, that's just an eigenvalue of the max matrix. Okay? And now, what I'm claiming is that when I look at the eigenvectors of the Lax matrix, this will give me the information about the location of the quasi-particle. And that's, of course, now a very rigid and nice definition, right? I mean, okay. Okay, and so the way how this goes is that you're saying that, so you take this eigenfunction, you think, I mean, so everything is time dependent now. I mean, so you think of this eigen, you take absolute value squared, I mean, just like if you do in quantum mechanics, and you think of this sort of like the probability that you know this quasi-particle alpha is sitting on the chase Toda trajectory, right? I mean, so you see, you have the Toda trajectories are labeled by J, but you know there are the positions Qj, and now you're saying that the quasi-particle is a little bit spread. And this spread is given by the absolute by the eigen vector absolute squared. This is normalized to 1, so that's a nice probability distribution. So let me just say it's one word about the literature. I mean, this was proposed some time ago, but you know they wrote down actually this problem. But I mean, and then wait one picture, but not very much. And then there was also a paper by Stefano Lepri, I mean, but he did something else. I mean, he was interested in sort of perturbing integrability but the person who really did a lot of mathematics out of this, and then he sort of, I mean, I have this formula from him. I mean, he somehow single-handed sort of, understood that this was a good definition, and then he proves theorems. I mean, so if you want to have sort of theorems, I mean, you have to look up these recent papers. I will just give you a flavor here. Okay, so now one important flavor is that, you see, you want to have if this is a meaningful definition, you don't want to have this quasiparticle to be spread over 200 sites. I mean, then where is the quasiparticle? So what is very important is that we have what in the physics literature called is the Anderson localization. I mean, these eigenvectors are with high probability sort of rapidly decaying, and the decay is sort of given in terms of this Lyapunov exponent. So the picture which I learned, when I was a student, was the following. I mean, so you do a boundary value problem. So you start here, let's say, with 0, 1, and then you sort of iterate, this 2 by 2 matrix, which exists in the Jacobi matrix. And of course, generically, I mean, you will exponentially increase. Well, you do the same thing at the other end of the string, you will also increase, and of course, you cannot really match the two. But if you precisely tune the eigenvalue, then they match, right? And then you can sort of continue and they solve the equations. Okay, so the main point is that under the GGE, I mean, this random matrix actually shows Anderson localization, and I think I have a picture of this, so you can see that. Yeah, you see. So here I see I plotted one particular eigenvector squared as a function of time, and so you see that it's sort of moving through, and it's typically localized on for our simulation, sort of like let's say something like 5, 6 lattice sites, right? And here you see a heat map of the same thing. I mean, so it's just the same picture, but this is all essentially 0. Numerically, it's 0. That's somehow the width of the quasiparticle. So this is how it's actually, right? I mean, so you can imagine that it's blurred. But you see, eventually we want to look at long-time properties, and the fact that it has an intrinsic width is sort of pretty irrelevant, right? But the important point is that it must have such a well-defined width, right? I mean, if I would have quasiparticles which are somewhat suddenly spread out over huge regions, I mean, then this wouldn't make much sense anymore. Okay, so I'm getting close to the end. I mean, so I'm not sure how we do with the time, but anybody has the time? Or?
Of course, to see the initial time. So, Robert,
we can stop in 5 minutes.
Okay, so what was that? How many?
5 minutes.
Okay, cool. No, this is fine. Oh, now.
Anyway,
to help me. Yes.
Total time is on the top, on the left.
No, but here. Why do that? Oh, okay. No, this was. Yeah, okay. No, it's fine. Okay, I should switch to that. All right. So let me just wrap up here. I mean, okay. So once you have the definition of the quasiparticle, I mean, you can of course differentiate in time. You get an expression for the velocity. And so here, what I show is the expression for the position of the quasiparticle, and here is its velocity. Okay. And now I'm saying that some of the things for which I want to show you some simulations that there are predictions from the theory, and you can compare actually the theory with these predictions, and there's some formal argument how people actually discovered this formula. You see, you want a formula for the diffusivity. I mean, you want to basically argue that the quasiparticle sort of looks like a Brownian motion. So let me just show you maybe the next slide here. No, this is not the next slide. Yeah, okay, that's okay. For some reason, transform. But here, what I plotted here is so here the bare one is sort of it's the bare velocity. This one is the motion of the quasiparticle, and it's sort of like a Brownian motion with a drift. So it has an average velocity, which is the blue line. And then you look at the velocity, and then you see it's sort of oscillating very roughly, and so it's not so unlikely the actual motion of the quasi-particle is described by Brownian motion with a drift. Okay? And this is one of the theorems of Agarwal. Okay. All right, so then I skip this one here. And now I want to, that's the final thing. So I want to show you just numeric simulation. Just sort of that you get some feeling for what we did. I mean, so, Alice 1000, we put thermal and we put sort of, various densities. I mean, the 0.06 is the free volume. So the last one is sort of extremely high density. I mean, they're really sitting very, very close. And that's sort of the signature of hydrodynamics, that in hydrodynamics, there's no restriction on the density. I mean, these laws are also true when things are extremely, there has to be fluid, of course, but otherwise it's still true. Okay. And so there's one thing which I wanted to communicate, which sort of is actually first sort of, we had to think about it. So if I take a particle system, I want to take a particle classically. What do? I color it red, and then I can follow this red colored particle. Now here we say, okay, they do the same. I mean, I put my initial conditions, then I have to compute the labels of the quasi-particles. These are the eigenvalues, and then I have to look, let's say, the eigenvalue closest to 0. Okay? But now I do another sample, and then I get a different value of eigenvalue. So I would have to condition on one eigenvalue to be 0. I don't know how to do this conditioning. I mean, not analytically, and also numerically, this is very hard. And so the resolution was that we do a binning. I mean, so we just cut the eigenvalues into little cells, which should contain sufficiently many eigenvalues so that you have decent average, but should be small enough that that we still see the variation, right? I mean, and then what we then find, of course, is the diffusivity directly as a function of the eigenvalue. Okay, and that's the last slide which I want to show you here. Okay, it's a little bit below. I mean, that's the most important thing. I cannot shift this up. No. Okay, anyway. So you have to imagine. I mean, so on top you see the density of states. Then these other curves are the average velocity. I mean, this is sort of not such a sensitive quantity. And what you see here below, I mean, so this one here, I mean, just you see, the value of the diffusivity. Okay, you see the value of the diffusivity, and within numerical approximation. I mean, of course, you see here, you see strong fluctuations because the density of states is already close to 0, and therefore, you will have too little samples in your bins. Okay, and so the conclusion is that one thing which I like very much, because it's sort of numerical simulations, but checking sort of well-supported theoretical conjectures, which of course for these systems are very hard to verify in an actual experiment. I mean, this is sort of, I mean, people do things like this, but that's a big sort of complicated story. But at least numerically, I mean, you can sort of verify these things. And here you see, I mean, there's no adjustment of equivalent. Okay, so thank you very much. Other questions?
No. Only at the level of the numerics.
Yeah.
Can one observe those things or ask those questions for something that's not integrable?
No, sure. I mean, no, I mean, people, I mean, you will find in the literature, you will find lots of simulations where they look actually at the non-integrable case. I mean, even in one dimension, but I mean, people have done well, I mean, for instance, I know of, I mentioned this class phenomenon. I mean, there's Abhishek Zaher. I mean, he run simulations exactly of this thing. I mean, actually, in this case, you see the Euler equations have sort of self-similar solutions. Because somehow delta gives from delta sig at the origin, And then he compared the numerical simulations with the self-similar solutions, and this sort of works very perfectly. So yeah, I mean, yeah, you know, people do much more complicated systems in higher dimensions.
Then there is no definition of quasi.
No, then there's certainly no quasiparticle. Well, I mean, I thought you were asking for the non-integrable case, right? Yeah, no, I mean, there are simulations. I mean, so for the integrable case, I mean, you know, there are realizations. I mean, people can sort of realize the delta Bose gas. I mean, these are sort of called atoms. The nonlinear Schrödinger equations, I mean, you do this optical fibers, and so you know, there are physical realizations, but you know, in order to see something like this and compare with theories, typically not a simple exercise. And the others, just talking here, but of course, you see, I mean, the quantum, the integrable community is mostly interested in quantum systems. Classical is sort of more like an attachment to quantum lines, so they really want to do quantum. Now, of course, quantum systems, in terms of simulations, are a disaster. You see, I mean, you can do 300 spins. I mean, that's considered to be a huge system. If you want to do a continuum simulation of the Schrödinger equation, I mean, just forget about these numbers, right? And so that's the power of these particular systems that you know, because it's classical, you have, you know, put in numerical tools to make, you know, precise comparison as I showed you.
Other questions?
What is known about dissipation? I mean, corrections to Euler. I mean, do these rigorous results, recent rigorous results, say something?
Well, for the hard work, there's a lot. I mean, the Coda is sort of the next complicated system, and at the moment, no, we don't even have the proof of Euler, right? I mean, and I think, well, I mean, for the hard work, of course, you have also results on the dissipated sphere. Right? I mean, that's yeah, but. Yeah, no, yeah, that question how it is. Right? I mean, so in some sense, you know, this work of Amal is sort of so the first step in direction to sort of, you know, make sort of rigorous mathematics of this sort of somewhat holistic explanation. Yeah.
No, but maybe there's some result of Bienen box model.
Okay, yeah,
okay.
Some experts, okay.
No, not experts. No.
But you know, yeah, no, okay, yeah, I should, okay. To make it more balanced, the answer, I should mention, you know, it's the box ball, I mean, which of course is beautiful theory, right? And which you can do, yeah, it basically can, yeah, in some sense you can do the sort of standard complete program, right? I mean, you prove the Euler equations, prove corrections, you look at particles. So for the box ball, I mean, you know, to even know what the quasiparticle is a tricky thing. You see here, I have a nice mathematical description which I can tell you in sort of in a half an hour. But for the box ball, I mean, you have to first know what you mean by quasiparticle.
Okay, we thank Herbert again. Now we travel backward in time to the Tullio Levi Civita Prize 2024. And now there will be another chairman, Mario.
Yes, okay. So, we start now without any small break.
Small break.
I should prefer
5 minutes.
5 minutes.
Not more.
No.
5 minutes. So, we start. So now we start to talk about Boltzmann. So it's Boltzmann in 1872. He wrote an equation, which is a basic equation, a Boltzmann equation, which was done for describing the behavior of rarefied gas, and starting from mechanics of particle systems. And this after Maxwell, and this was interesting also because there was a sort of apparent contradiction between the time reversibility of the microscopic system and the irreversibility of the macroscopic equation. And there was a debate. Some people say that the equation was not true, not consequence of mechanics, and so on. And much later, Harold Grad in 49 of last century predicted that the Boltzmann equation should be valid under some scaling limit, namely for particle system and particle with the diameter epsilon. If you take a sort of low density limit, namely L epsilon square constant equal to 1, for instance, and take the limit and go into infinity, the Boltzmann equation should follow from the particle system. And this was important. And this was in 49. And Boltzmann himself had in mind something similar without describing it quite precisely. And finally, in 75, last century, Oscar Lamford gave a proof of the validity of the Boltzmann equation, but only for short times. And this was important result, and followed other important result, one by Carlo Cercigliani, who wrote down the exact wrote the equation for the system of R-spheres, that is the simplest case to deal with, and the result, important result by Giovanni Carlavotti, who gave a derivation of the Boltzmann equation global in time, but for a linear system, so a test particle in a random distribution of scattering, with a very important result. So after Lamford, there were many other results concerning important contribution by Herbert Spohn, that was here. And so there were other results that I cannot mention here. And then recently we got some unexpected, very important result, giving a proof of the global validity of the Boltzmann equation. Namely, suppose that you know that the Boltzmann equation has a good solution up to the time capital T, then particle system are spheres, that is the simplest case, can approximate the Boltzmann equation. This result was spectacular, unexpected, because some point, I don't know, there was the general feeling that short time was very, very difficult. And it was obtained by Zaher Hani here in collaboration with Yu Deng and Mas. It's very important and important result. This result actually followed the other result by Zaher and Yu Deng on the kinetic description of waves, and it was an important tool for dealing with this. So I'm not describing the full activity of Zaher. So what I mentioned, what he probably is going to discuss today, only this important result. From my point of view was really expected, surprising and important result. Now, Zaher Hani is professor of mathematics at the University of Michigan right now. He got his PhD in 2011 from USLA and worked under the direction of Terence Tao. And he was after at the Current Institute for Postdoctoral Studies. Then he got a position at Georgia Tech, and then he moved in Michigan. And he got some prizes that I will not mention. But he's a good colleague, and I must say that today I'm particularly happy. Let me do some personal consideration. We are doing this official, but both Herbert and Zaher, not formal person. So I mean, I feel free to joke, to do something in a complete free way. So thank you to be here, both of you. And Herbert talked about something different, but he gave important contributions to the same field. So it's for me, it's really a pleasure to have books from you. Please. I'm sorry.
Se ti mettono un po' più là, la videocamera li vede, se gli date le spalle non può girare.
No, I'm sorry. What I have to do? Yes, please.
We put a picture, I guess.
Thank you.
Put a picture. Look there.
Thank you.
Well, of course, first of all, thank you for all of you. I'm very honored by this prize, and it was a great pleasure, always a great pleasure to visit here. First time I visited here was last year when I met Mario and Sergio, and it was started a very fruitful and interesting discussions, and I thank them again for inviting me this year. And again, I'm very honored by this award. And I have to say that I'm doubly honored. My honor is doubled to be with Herbert as well. Herbert also was a very influential figure for me in particular. When I started working on wave kinetic theory, there were basically zero mathematical results apart from Herbert's work. So Herbert's work was really the North Star for me. And if it wasn't for that, I probably wouldn't have done anything on wave kinetic theory, and probably I wouldn't have done anything on Boltzmann, and I wouldn't be here. So thank you, Herbert. And again, I'm very honored to be here with you. Okay, so let's move on to the mathematics. So I'll be talking about the long-term derivation of kinetic equations, and this is as Mario mentioned, this is joint work with Yu Deng at Chicago and Salma at Michigan. Okay, so this is falls under a broad umbrella of Hilbert's sixth problem, and this is something that we will discuss in some detail over this talk, what this problem really means. And this was, of course, announced in the 1900 ICM, and asked for the axiomatic derivation of the laws of physics. So some of you are familiar with that. So the key dream, if you like, was to start from fundamental laws of physics as axioms, and you want to derive from them with mathematical precision other laws. And of course, if you broadly interpret that, this is the scope of this problem is all of mathematical physics, really. In his follow-up paper, Herbert specified two concrete questions under his sixth problem. One of them was the rigorous foundations of probability, and the other one relates to Boltzmann's kinetic theory. And there he says, the problem of developing mathematically limiting processes, they're merely indicated, which lead from the atomistic view to the laws of motion of continuum. And let us try to explore what this means. So what does it mean to go from the atomistic to the continuum? We want to start from Newton's laws on uncolliding particles. This is the microscopic picture, as you all know. We want to take the kinetic limit to get to the Boltzmann picture, which is the mesoscopic or intermediate scale. And then we want to take the hydrodynamic scale to get to hydrodynamic equations. Okay, and this, we will refer to this as Hilbert's program. The interesting thing about it is that it features a passage from something that is time reversible to something that's time irreversible. So there's a creation of arrow of time. But we'll talk later about some limitations about this, this program at the end. So the type of hydrodynamic equations that you get are a very special kind of dynamic. Okay, and it's safe to say that this second limit was fairly well understood in the past century. And by the contribution of many people. I mentioned some of them here. So the main difficulty was really in understanding this first kinetic limit. Okay, so to understand what is the mathematical problem here, so we review Boltzmann's kinetic theory, where you start with a system of particles. Each of those particles has a diameter epsilon, and those particles are undergoing elastic collisions. So they come into the collision with the incoming velocity Vi and Vj, so this is Vi in and Vj in, and then after the collision, they come out with outgoing velocities, Vi out and Vj out. And of course, the vision of Boltzmann is, let us not solve the Avogadro's number of equations that is satisfied by each particle. Can we give a statistical description of the system, such as the effective dynamics of the one-point density function? Okay, this is to think of it as the probability of finding a particle at position x moving at velocity v. Okay, and the hard sphere system, these are Newton's, they satisfy Newton's equation, and of course, so the first equation is just straight motion in a straight line, that if a particle does not collide with any other particle, if the centers are at a distance greater than epsilon, which is the diameter, then the particle will move in a straight line. And if a collision happens, then this is, we impose the elastic collision conditions that that give you that the outgoing velocity is related to the incoming velocity by those relations that are given over here. So here, xi, so nu is the unit vector in the direction of the centers of the two particles, and these follow just from writing down conservation of momentum and conservation of energy at an elastic collision. So this is so this makes this into a time reversible volume preserving dynamic system. Okay, so we are really starting from something that is time reversible. And Boltzmann's theory takes this statistical approach or statistical point of view. So what we'll assume is that exactly as Herbert mentioned, is that you assume that initially you start from random data, and those random data are distributed in a particular way where you assume essentially, roughly speaking, that the different particles are independent of each other. What this means is that if you look at the endpoint density function Fn, this is the probability of finding particle 1 at position velocity z1, particle n at position velocity zn. So we'll use zxv in order to denote the position velocity vector. Then this endpoint function is in what we call the factorized state. So what this means is that this is given by product and full product of a function, which is the initial one-point density function. And then we have to normalize it so that the total probability is 1, and we also multiply by the characteristic function of the domain of propagation, which just tells us that the distance between any two centers is greater than or equal to epsilon. Okay, there are some things missing in the, here, let's see. Okay, so the kinetic theory, which is something, so Grad told us as Mario mentioned, Grad told us that those limits cannot be taken arbitrarily. You don't take n to infinity epsilon to 0 an arbitrary order. They have to be taken in such a way that n epsilon to d minus 1 is order of 1. So this is here what's not appearing on this slide for some reasons, that this is n go to infinity and epsilon goes to 0. Okay? So this is the Boltzmann-Grad. And then we get to Boltzmann's theory. It tells us that, okay, so at time t equals 0, the particles were independent of each other. As time goes by, this independence is not preserved because the particles collide with each other. So this factorization is not something to expect to be preserved at the microscopic level. However, the first element of Boltzmann's theory is what we call now propagation of chaos, or the molecular chaos assumption. And it says that this factorization is actually stored at the mesoscopic scale, at the kinetic scale. In other words, that if you take the limit of n going to infinity and epsilon go to 0, then after you take this limit, this factorization is preserved. This propagation, this chaos is preserved. And what this means is that after you take the limit, you only need to track the behavior of the one-point density function. You don't need to track the behavior of the higher density function, because those are just products of the one-point density function. Okay, and the one-point density function is something that we can actually track its effective behavior, and this is given by Boltzmann's equation over here. Okay, so presumably everybody has seen that before. This is the collision kernel. This is the quadratic collision kernel, where we use the notation when f prime means that I'm evaluating f at v prime, and and v and v1. V is fixed by the right hand side. V1 is the other incoming velocity. So the picture that you have over here is something like this. This is v, this is v1, and this is v prime and v1 prime. Okay. And yeah, so and they are related, v prime and v1 prime are related to v and v1 by the same conditions that we had on the previous slide when we were over here, when we were talking about elastic collision scattering conditions. Okay. Okay, so the timeline of this theory, again, this is something that is, I don't mention everybody. This is just a non-exhaustive list of contributions. Of course, there's the first contribution was to Boltzmann to derive this kinetic equation, assuming the molecular chaos assumption. Then Herbert proposed this derivation as a way to obtain fluid equations. And then we talked about contribution of Grad in specifying the Boltzmann-Grad scaling law. And then there was work of Chirchiriani, who introduced this approach, that we call now BBGKY approach to the derivation. So this is basically a hierarchy of equations. You write down a hierarchy equation of the S-point density function and try to analyze that. It's not, I'm not elaborating much on this approach because it's not the approach that we will take. And then using this approach, Lanford in 1975 gave the sort of biggest landmark of the past century on this in this field, which gives mainly the derivation of the Boltzmann equation, the rigorous derivation of Boltzmann's equation. So this means that if you look at the one-point density function of the particle system, the probability of finding a particle at time t moving at position x and velocity v, then this thing converges to the solution of the Boltzmann equation in the limit, in the Boltzmann-Grad limit, and going to infinity and epsilon goes to 0. And this is what we mean. This is what we will mean by a rigorous derivation of the equation, showing that the one-point density function of the particle converges to the solution of the Boltzmann equation. The main caveat of this result is, of course, that it came with a time restriction that it only worked for short times. Okay. And then there was a lot of work. Again, this is non-exhaustive list. There was work of Illner and Fulgranti in the 80s, who gave a long-time derivation in the near vacuum setting. Then there was work in the 90s by Mario and collaborators and others, where those kinetic and hydrodynamic limits were studied for stochastic particle models. Things become a little bit more tractable in the case of stochastic particle models. Then there was work in 2014. The problem of the Boltzmann equation was reinvigorated in 2010 by Gallagher, Saint-Raymond, and Texier, who revisited Lanford's proof and proved some explicit convergence rates. Then there was work by Bodino, Gallagher, and Saint-Raymond, who studied microscopic limits at equilibrium that are based on linear or linearized Boltzmann models. This is, again, based on earlier works of Spohn and many others before that I do not cite. Then Sergio joined this group from 2018 to 2024, and there was a very successful and long series of results that studied fluctuations around the Boltzmann limit. So that you understand the Boltzmann limit as a law of large numbers, and then you try to ask what is the corresponding central limit theorem around that. Okay, and this is again done either for short times or in linearized settings. Okay, and then this, of course, leaves us with the main question: is that all those results were restricted either to short times, either to near vacuum settings, or linear settings, and in particular, this does not allow us to effectively link the two kinetic limit and the hydrodynamic limits. Okay, because the hydrodynamic limit is really based on solutions of the Boltzmann equation that are not near vacuum and those solutions that exist for long times. Okay, so the question of deriving the Boltzmann equation for long times or giving a long time extension of Lanford's program was really a central question. Okay, so this brings us to the main results. So this is almost the first one almost 2 years ago, and the second one was last year. So we consider a hard sphere system in dimension d greater or equal to 2. On Rd, if we are studying it on Rd in any dimension d greater or equal to 2, on the torus, we require either 2 or 3. And we assume the Boltzmann grad scaling. Then suppose you give me a solution of the Boltzmann equation that exists on a long time interval, an arbitrary long time interval, 0t final. Then we can give the derivation of the Boltzmann equation on this long time interval. In other words, if you give me any s and any time between 0 and t final, then if I look at the s point joint density, this quantity, which is the probability of finding particle 1 at Z1, particle 2 at Z2, up to particle S at CS, this is something that is well approximated by the S-fold product of the solution of the Boltzmann equation. Okay, and the convergence is in a strong L1 norm. Okay. So the regularity assumption of the Boltzmann equation are basically the same as in Lanford's proof. We require that the solution is L1 in X, so that it's a probability density, and Maxwellian weighted L infinity in V. The theorem holds both on Rd. This was the 2024 paper, and or TD and D equals to 2 or 3. And these are exactly the type of results that you need in order to extend this derivation of the fluid equations. So you can combine those results as black boxes with existing works on hydrodynamic limits in order to give the rigorous derivation of the fluid equations like compressible order and incompressible order in the Boltzmann grad limits. Okay, so this is a sample of such a results. So we consider the hard sphere system in dimension D 2 or 3 under the Boltzmann grad scaling. Now I have to make this into a parameter. This is n epsilon to d minus 1. This is the collision rate. This would be a parameter that will need to go to infinity in the limit. And if I consider a solution of the compressible Euler equation on this and on arbitrary long time again, we define the local Maxwellian as such. Then we have that the 1-point density is well approximated by this local Maxwellian, and the difference is bounded by this quantity alpha inverse. So in the limit of alpha going to infinity, you get this difference is 0. And this is what we mean by a derivation of the equation. And so one can formulate a similar result for the incompressible Navier-Stokes. Okay.
Excuse me. The previous result was stated with alpha equal to 1.
1, yeah.
And the other estimates depends on alpha.
Yes.
So how this the first result depends on alpha? The estimates in L1 for the first limit depends on alpha. You can close
Yes, you can. So strictly speaking, I can't put alpha over here. So this is what you do is that you do put alpha over here, okay? And then the contribution of the first result will appear as something that depends on alpha, but also multiplied by a power of epsilon. So the point here is that I'm really taking the limit of epsilon going to 0 first, and then taking the limit of alpha going to infinity.
Okay.
Okay, so it is a subtle thing. So what I'm doing over here, in order to get this limit, I take the limit of epsilon goes to 0 first. I fix alpha, take the limit of epsilon to 0 first, and then I take the limit of alpha going to infinity.
Okay.
Okay, there's more general limits that you can take. I can allow alpha to depend on epsilon, but in a very, very weak way, like a log of epsilon to the 1/2. But for this statement over here, I'm writing it in such a way that you have to think that I'm taking epsilon to 0 first, while alpha is fixed, and then letting alpha go to infinity. Okay, so
It's a good question. You need that the Fourier part must vanish.
Yes, so in Navier-Stokes, you start with perturbation of the global Maxwell. Yes, absolutely.
Sorry, at time 0, you just assume the same form.
Sorry?
At time 0?
At time 0,
Yeah,
I mean, you have to prepare your data properly. There's some Hilbert expansion that you assume at time t equals to 0 for f1 epsilon, which at first order is equal to this. At first order is equal to this, and that at higher orders of alpha inverse, you get some things that are given by the Hilbert expansion.
for the previous theorem?
For the previous theorem, no. Of course, this is for the previous theorem, just the same, the initial data for the particle system. So this F initial over here just has to be the same initial data for the Boltzmann equation. That's all the requirement that you take. Okay. All right. So we sort of got to this working on particle kinetic theory in a funny way, because we, or at least I and also my collaborators, were not working on this. We were working on the wave counterpart of this theory. We come from, our background is waves, and in particular over the past maybe 12, 13 years, I have been very much interested in putting the theory of wave kinetic theory, sometimes it's called wave turbulence theory, on rigorous mathematical foundation. So this theory is based on, you replace colliding particles by interacting waves. So instead of particles colliding, you think of waves interacting to each other. And instead of Newton's laws, which tells you what happens when two particles collide, you replace that by some wave type equation that tells you what happens when waves interact. Okay, so for example, in some sense, the central model that you always should start with in this theory is the nonlinear Schrodinger equation. It plays the role of hard spheres that hard spheres plays in the particle theory, and it is really intimately related to the hard sphere theory. And so this is given to you by IDT U plus Laplace U is alpha U squared U. So you have a cubic nonlinearity, and you pose the problem on a box of size L, a periodic box of size L, or the torus of size L, and then you have, so this is one of the parameters in the problem, so the size of the box L, which will go to infinity, and the size of the box will be the analog of the number of particles going to infinity in Boltzmann's theory. And the other parameter, the asymptotically vanishing parameter, is the strength of the nonlinearity alpha. Okay, so alpha will be going to 0, and this will resemble the diameter of the particles going to 0 in Boltzmann's theory. And under a suitable limit, again, the limit has to be taken in a particular way, of L and alpha, you get a wave kinetic equation, which in the homogeneous setting where you don't have spatial dependence on your initial distribution, statistical distribution, you get dTF. If you do have spatial dependence on your initial distribution, then you get the usual transport term on the left-hand side. And on the right-hand side, you have a collision kernel, which is now cubic. So it sort of looks very much similar to the cross-section of, it's actually the same cross-section as the Boltzmann for hard spheres, except that you have a cubic, it's a cubic rather than being quadratic. Okay? So, okay, and then, yeah.
The relation between U and F.
Yeah, that's a good point. So F is supposed to be F of Tk is supposed to be the average of U hat of Tk squared.
Okay.
Okay, so this is the variance of the Fourier modes, and it's the variance of the Fourier modes. Okay, so following some foundational works, particularly by Herbert, and then there was a rigorous work of Lukarinen and Spohn in 2011 on the problem at equilibrium, where you study time correlations. I started working on this in this direction. First, we tried to understand how to take mathematically this large box limit and the small nonlinearity limit in a couple of works, which was it's a non-trivial question from a mathematical point of view. And then in this 2017 work, we took the first step in considering the full problem, so studying the derivation problem of the kinetic equation starting from non-equilibrium initial data. And we derived the equation for very short times, much shorter than what the physical theory predicts. And then we improved those times in my first work with Yu Deng in 2019. And independently, this was also done by Collin and Germain in 2019. But then the first challenge was to give a rigorous derivation of the equation up to short kinetic time. So an analog of Langford's theorem in this setting. And this is something that we did in a series of works with Yu Deng from 2021 to 2023. Where we gave the rigorous foundation of this theory, we derived the equation and proved the propagation of chaos as well, and this was essentially the short-term theory. Okay. Then in 2023, we succeeded in extending this derivation to long times, and so we derived the wave kinetic equation for arbitrary long time. To have a theorem very similar to the theorem that I gave you for Boltzmann, assume that the solution of you have a solution of the wave kinetic equation, then we can derive this solution as a limit of the behavior of the microscopic system, as a limit of the microscopic system. And as far as we know, this was the first result of its kind, and this is really what gave us the strategy in order and the motivation to study the Boltzmann problem. The proofs that I will start telling you about for the rest of the talk are essentially, at the conceptual level, they're exactly the same. Everything that I will say it in the language of particles, but everything that I will say translates verbatim to the language of waves. There are key technical differences between the two proofs, but I am never able to get to those differences in a 1-hour talk. So everything that I will tell you about holds exactly the same for both the wave and the particle setting. Actually, I actually debated about giving this the proof and writing the rest of the talks in a unified way for the waves and particles, but then it somehow took more time than I wanted it to take. Okay, so I'll just use the language of particles, which I feel is more intuitive as well, okay, to tell you about the proof. Okay. So all those proofs are based on diagrammatic expansions. So So these are basically, you have two solutions here. You have the solution of the microscopic system, and you want to show that this solution in the limit is effectively described by this kinetic equation. So you have a solution of the kinetic equation and you have a solution of the microscopic system. Of course, the solution of the microscopic system is much more complicated, it's much more elaborate compared to the solution of the kinetic equation. So what you do is that you expand both solutions as Taylor series, essentially, at time t equals as Taylor series. Okay, so you have an expansion of the microscopic system, and you have a much simpler expansion of the kinetic equation. So the expansion of the microscopic system, here you have a choice on what kind of expansion you make. Most of the previous work did this BBGKY approach to the expansion that was pioneered by Ceciliani and used by Lanford. We will use a different approach based on cluster expansion, so another classical idea in statistical physics, rather than the BBGKY. And in some sense, the first idea of the proof, so you have this expansion of, let's see which one works. How this works. So you have an expansion of the microscopic system. And you have a much simpler expansion of the Boltzmann equation. And at first, you want to identify the terms over here that converge to the Boltzmann equation. The same thing happens in the wave theory. And the main challenge is to show that everything else goes to zero. So these are leading terms in this expansion. You want to show that they converge to the expansion of the kinetic equation. This is the first step, and usually this is one of the easier steps of proofs. The challenging step is to show that everything else goes to zero. And the point of showing that everything else goes to zero over here is to bound, for example, this time series expansion as something like c to the n, t to the n, from n equals 0 to infinity. And of course, this is, when you do such a bound, you're dealing with power series. When you do such a bound, you have this restriction that t is less than 1 over c. And this is where the short time restriction in Lanford's theorem comes from. So it's a very natural restriction. It's really, you're doing a proof that is based on power series expansions, and power series have a finite radius of convergence. Okay, so this tells you really what is the problem in extending this proof to longer times. And this is just like you're really dealing with an analytic function like 1 over 1 plus t. And in some sense, you want to think of the function 1 over 1 plus t, but you want to think of it at time t equals 10. You don't want to think about it at times between -1 and 1, where it is equal to its Maclaurin series. You want to think of it about time t equals 10. And in some sense, since diagrammatic expansions are the only idea that we have, we want to think of it about at t equals 10, but we also want to expand it as a power series or some Taylor series. So the only solution to do that is to do this time layering. So this means that you want to split the time interval, the long time interval 0 t final, into sub-intervals that are short enough. How short? So we want to split it into time interval that is short enough such that the Boltzmann equation, this expansion over here, I can make sense of it, each of those short time intervals, but with a different base point. So this is like, think of the function 1 over 1 plus t. I'm expanding it in Taylor series, but not necessarily centered at 0, centered at 1, 2, 3, etc. Okay, and since I have global a priori bounds on this Boltzmann solution, I can pick this tau uniformly. Okay, it might be small, but I can pick it uniformly so that on each time interval, I have this power series, or not power, but Taylor series expansion of this equation on each such subject. Okay, so this, in some sense, you can think of it as that this resolves the divergence problem, this long time divergence problem for the simpler expansion over here. But of course, it does nothing for this more complicated expansion of the microscopic system, which is much more elaborate. Okay, and then you start thinking about this. So then you notice, we start thinking and we notice that the only reason that this expansion converged on the short time interval 0 tau, this is Lanford's theorem, was that because we assumed that at time t equals to 0, the particles were independent of each other. We assumed that so we start from a factorized initial state at time t equals to 0. And I already told you that at time t equals to tau, you do not expect this. This is not factorized. Okay. So in order to extend this expansion to longer times, so to times, say, go to the next time step, tau to tau, I need to understand how much independence did I lose in this first time interval. At time t equals to tau, how much did I lose of this independence that was at time t equals to 0? And again, there's an object in statistical physics that measures that, which is the notion of cumulants. Okay, so these cumulants are precisely things that measure how much independence did you lose. Okay, so for a set H of particles, the cumulant, this is what I'm using, is sometimes called truncated cumulant. This cumulant EH measures how likely the particles in H, how likely that they got correlated to each other on the interval 0t. I will not give the explicit definition here, because intuitively the only thing that I want you to remember is that this is what the cumulant EH does. It measures how much the particles inside H, okay, have gotten correlated to each other on the time interval. Okay, the key formula you use is something that we learned from a paper of Mario and Sergio from 2016, and Mario tells me this is based on earlier work of Presutti, which tells you that if you look at the S-point density function, then this is given by a factorized state. Okay, so this is what you want in the limit, what you want to prove in the limit, plus the contribution of cumulants, okay, which is given in a more complicated way that involves this. Okay, so this function G is, you can think of it as the one-point density function. It's not precisely, but you can think of it as that, and it approximates the solution of the Boltzmann equation. So the proof now boils down to showing that this contribution of the cumulants is 0 in the limit, okay? And showing that G converges to the solution of the Boltzmann equation. Once you show that, then you have shown that the S-point density function converges to the S-fold product of the Boltzmann equation. This is, which is the theorem. Okay. So, so to tell you a little bit about the intuition behind this cumulant expansion, as I said, we get to this cumulant expansion by using a slightly different approach than the one that Mario and Sergio took before. We'd use this idea of cluster expansions. And the idea here is that suppose you are looking at the 3-point density function at time t equals to tau. So you have 3 particles, 1, 2, and 3. And what we do is that you just look at all the possible interactions that those 3 particles could have with each other and with the rest of the system. Okay? So there are many possibilities, but you can arrange those possibilities in diagrams. So here is one of those possibilities. So in this possibility, this particle 1 collided before with particle 4, and before that, particle 4 collided with particle 2. Whereas particle 3 did nothing related to particles 1 and 2, did not interact at all with particles 1 and 2. It interacted with particles 5 and 6 as above. Okay? So in this, if I look at the time t equals to tau 3-point density function, I will get some sort of correlation between particles 1 and 2, because those 2 particles really got correlated to each other on this time interval. But then particle 3 will be somewhat independent of them. And you do this kind of analysis for every possible interaction history that involves those 3 particles. This is what cluster expansions is really about. And this is what gives you the expressions and the expansions for the cumulants. Again, there's an important twist here that you have to do, is that if you do this naively, you will diverge because we are dealing with long time intervals again. So there's a trick, which is really a renormalization trick that we call partial time series expansion. And this is crucial in order to get a series that does not diverge on the long time. Okay, I don't think I have time to explain this here. But here's the central point that you get to. So this is the first, after this first part of the proof, you get into a diagrammatic expansion of the cumulants. You can represent the cumulants as a sum over diagrams. Okay, this is it's really representing the cumulants as a sum over interaction histories. Okay, and this is what is written over here. So if I look at the size, the L1 size of the cumulants, and remember what I want to show is that this is something that goes to 0 in the limit. I can write it as a sum over, think of this sum as a sum over interaction histories that involve those H particles, okay, in EH. Okay, I have H particles. I'm talking about the cumulant EH, which means that there's an underlying assumption that those particles got correlated to each other in the time interval from 0 to L tau. So this is the L layer L tau. Okay, so I'm summing over all possible collision histories, okay, and I will tell you how I will represent it of a quantity I of m, okay? So let me talk first about this collision history. So this is, we call them molecules. This is, again, a notation that we used in the wave setting and we carry it over. These are just graphical, at the basic level, these are graphical representations of the collision history. So this is an example of a collision history where this particle collided with this particle, and before that, this particle collided with this particle, and before that, these two particles collided. So at the simplest level, what we do is that whenever two particles collide, we put a node in a graph. We define a vertex in a graph. So I have 3 vertices over here. And then the linear motion between two collisions, I represented by an edge in this graph. As at the most basic notion, this is how we represent those molecules. And as a result, this I of m over here becomes the probability of the interaction history that is described by this graph m, or this molecule m. What is the probability of this happening? Okay, so this is m is the representation of a collision history. I of m is the probability of this collision history. Okay, and we're measuring probability according to the initial density. This is the only random thing that I have is the initial density. I have a random distribution of the initial density. Okay, and this brings us to the central point and the central object of recollision. This is something that Boltzmann himself understood was really a central point. Recollisions now appear in this diagrams as loops. Okay, so this is a cycle. So like over here, you have a closed cycle in this molecule. So you have the green particle collided with the red particle, and before that, the red particle collided with the blue particle, and before that, the red particle collided with the green particle. This means that the green and red particle met twice. This is a recollision. This is what we would call a recollision. And why are recollisions the central object here? They are for the following reasons that I write over here. So recollisions, they cause a divergence in this sum over here. In other words, if you allow more recollisions, then the number of interaction histories that are possible diverges. So more recollision means that more ways that the particles can interact with each other. It makes sense. But if you are to believe in Boltzmann's theory that these cumulants goes to 0 in the limit, then this divergence has to be balanced by a gain in the probabilities I of m. So what this means is that you want to show that if an interaction history involves many recollisions, then the probability of this interaction history happening should be low. Okay? So it is really this balance between the divergence on the number of histories that involves many recollisions and this being balanced by the probability of such a collision history. And the whole point of the proof is to quantify this inclusion. The whole point of the proof is to quantify this inclusion. Measure precisely how this divergence, how much, if I have row recollision, how much this sum diverges, and if I have row collision, how much I gain from the probability of such an interaction. Okay, so the key point is to really measure this gain. How much do I gain from thinking about the probability of an interaction history or a collision history that involves a certain number of recollisions. And the basic operation to estimate I of m, remember this interaction history could be very, very complicated. I mean, we're not putting much limits like on how complicated this is. There are some limits, but nothing that is forbids it from being still very complicated. So basically, you need a mechanism in order to reduce and understand this I of m. Okay, this I of m is really an integral expression that is based on this very large molecule. Each edge of the molecule gives you a variable, and you have an integration over this variable of integration. And the basic reduction mechanism is cutting. This is also something that appears in the wave case under different naming. So the basic idea is that you do a cutting. So you, for example, this is an example of the collision history, and I cut this. I cut it into two parts. This molecule, I cut it into two parts, part M1 and M2. And if I do this cutting correctly, and by this I mean the following. That's so easy to. So if I have an edge and I want to cut it over here, so what this means is that I do this cutting, but the point is that when I do this cutting, I have to, each edge is associated with a variable of integration. So this is something like z corresponding to this edge. When I do this cutting, you create two edges, say ZE1 and ZE2. And the point is that you have to assign that one of them is fixed and the other one is free. Okay. So fixed means that essentially you're not integrating against it. There's an integral associated with this. Free means that you're integrating against it. And this is nothing but a graphical representation of Fubini's theorem. There's nothing really deeper here. So in Fubini's theorem, when you do a double integral, you first fix one of the variables and you integrate in the other, and then you integrate in that other variable. This is really what we're doing. We're fixing this variable, integrating in the other variable, and then you sort of integrate in the other variables, and then you integrate in this variable. Okay, so this is really, it looks like something that is magical, but it's really nothing more involved than Fubini's theorem. It's just a graphical representation of Fubini's theorem, because in the end, this I of m is just a large integral, and you want to understand a large integral. The only way to understand a large integral with many variables is to organize how you are doing Fubini on this large integral. Okay, so this is the strategy. So this cutting over here is just a representation of Fubini's theorem, and the strategy now is that, assuming I have a rather large diagram, I want to cut it into elementary components. So these are, I want to keep on cutting this very large molecule until I'm left with only small parts. And by small parts, I mean parts that involve one or two collisions at most. And why is that nice? Because for molecules that have one or two collisions, I can compute their probability by hand. Okay, the integral becomes rather fairly sufficiently simple so that we can compute it by hand. Okay, so if we do this cutting of a very large molecule into small molecules, mk, m1 up to mk, then I can recompute or estimate the probability of the original molecule by just as a product of those probabilities of the smaller molecules. Okay, so this is the main reduction mechanism that we use in estimating I of m. Okay, and remember the thing that we started with and what we wanted to show is that if I start with a collision history or a molecule m that has a certain number of recollisions, I want to get gains out of those recollisions. And I want to get gains out of those recollisions from this mechanism over here. Okay, so the next thing I want to tell you is, I want to tell you how those gains appear. And to tell you how those gains appear, I want to tell you about those elementary components. There are special elementary components that come with gains. Okay, and as I gave a very similar talk to this last year at a conference, and I'd like to explain them in using the language of billiards. Okay, so this is the most important elementary component, where you have one collision and the final destination of one of the particles is fixed. Okay, so this is similar to just having to put this ball. You want you're playing billiards and you want to put this ball in one of the pockets. So the final destination is fixed over here, and this ball has diameter epsilon, and you want to hit it with the white ball, as you all know how billiard does. The probability of making this shot is epsilon to the d-1, and this is basically because in order to hit the red ball, you have to sort of fix the angle of your stick in a window of size epsilon of SD-1. Okay, if you're outside this window, you're not going to hit the red ball, and as a result, the measure of this window of size epsilon SD-1 is epsilon to the d-1. So the probability of making this shot is epsilon to the d-1, and this is the most basic elementary molecule. So this is what we call an elementary molecule. This is a molecule that involves one collision. This is the most basic one, and if you can do your cutting of the molecule and you only get those, then you will get the leading order terms in your expansion. This kind of molecule is intimately related to the Boltzmann equation. Okay. However, there is another very important molecule. This is the molecule that comes with the gain, that gives you the gains, where you have two collisions. Okay, so you have three particles, two collisions, and the final destination of two of the particles is fixed. So I can translate it as into a billiard shot where I have two red balls, and I want to hit those two red balls with the white ball such that the final destination of those two red balls is fixed. Okay? So I want to do one shot of the white ball. So the white ball has to hit this first red ball and put it in this pocket, and then it has to hit the other red ball and put it in this pocket. Okay? And of course, the probability of this, the naive estimate on this probability is also epsilon to the d-1. Okay? But this is a naive estimate because we all know that in order for you to make this shot, you need to be a much better player, and the probability of this shot is much smaller. And you can compute the probability of this shot because this is still an integral that you can really compute. It takes a few pages, but you can compute, and you can get a gain compared to the naive estimate of epsilon to the d-1. The gain is even better than 1/2, but 1/2 is enough for today. Okay, so this is what we call a 3,3 molecule, and this is the smallest unit of gain, right? So remember what my strategy is to take a large molecule, cut it into smaller molecules, and we realize that if I get a small molecule like this, then I'm getting a gain. So this means that I want to maximize this number of molecules that come with a gain. Okay, and this is in order to do that, this reduces to setting up a cutting algorithm that maximizes the number of those good molecules and minimizes the number of bad molecules. There are bad molecules that I didn't tell you about. And the rough idea is that if you have many recollisions in your molecule, then those recollisions require you to make many of those two pocket shots. In other words, you should see, if you have row recollisions, row loops in your molecule, you should recover a good number of those, like something comparable to row of those 3,3 molecules. And at the basic level, you can see it here. This is this is a loop, and I did a cutting of this loop over here, and you can see how a 3,3 molecule appeared in this cutting. So these 3,3 molecules are very much intimately related to the loops, and this is the point of this algorithm. That guarantees that if you do this cutting, you can do this cutting in a smart enough way such that you get a sufficient number of 3,3 molecules, and you get a small number of lossy molecules, and such a way that you get something comparable to the collisions. And this is probably the most technical part of the proof. This is the most complex part of the proof. There's again, in the wave setting, it is also the most technical part of the proof. But somehow in the particle setting, this combinatorial part was more challenging in the particle setting. Okay, so last slide. Now I want to discuss what what I think Hilbert's sixth problem means now, and what remains to be done on Hilbert's sixth problem. And you will see that essentially everything remains to be done on Hilbert's sixth problem. At least even if you narrow your perspective to the perspective of deriving the fluid equation. We really are still don't know most of things. Okay, so there are many things to be done. First thing are to understand other kinetic limits. So for example, here, I only told you about hard sphere collisions. We do have some understanding, and we can even extend our result to cases when instead of hard sphere collisions, should be possible to understand to extend it to potential interactions such that the potential is compactly supported. So for the short time theory, this was done by King, and then done in a proper way by Gallagher, Saint-Raymond, Texier, and for Volenti, Safira, and Simonella. So this only holds for short range potentials, and by short range I mean compactly supported. Okay, those results should be possible to extend to long times, but the key point is that we have no idea how to deal with more general potentials, even for short times. Okay, this is a big challenge for the future, for 21st century. Then there is the quantum settings. What happens if we replace classical particles by quantum particles? And again, in this case, there are partial results. There are work of Benedetto, Castella, Esposito, and Pulverenti, the work of Erdős Yao. Just last week, there was a paper by Marston, Nam, Herbert, and Tran, who did the equilibrium setting of this problem. So you start with a Gibbs, some sort of a Gibbs measure initial data. But again, this problem is very open even for short times. Very interesting and very open for short times. Then there is the derivation of Landau equation. The Boltzmann's equation are not the only important kinetic equations. So there are kinetic equations that appear in sort of weak, in the weak coupling limit, like Landau's equation. There are partial results by Bobilev, Mario, and Chiara Safirio, but again, this is still open for short times. Okay, in terms of hydrodynamic limits, also we are far from being in a satisfactory position. So we have the main problem, and this is really a problem in Hilbert's program itself, is that if we want to pass to the hydrodynamic limit through the kinetic equation, then we are left with a very particular type of compressible Euler equation. This is the compressible Euler equation with an ideal gas law. Okay, so then the natural question is, what about more realistic gases? So what if I have a gas that is not as dilute as that in Boltzmann graph? What if n epsilon to d minus 1 is not order of 1? Even if I add over here, or I subtract a very small delta, we don't know how to do that. Okay, and then in some sense, the big question is whether we can derive compressible Euler under real gas laws. Okay, here there's a program of Morey that, again, there's a question whether it can be done in a rigorous way or not. Okay, so this is a big challenge. And then other big challenge, which I think is very much related to this direction of deriving rigorously those fluid equations, is to get a proper understanding of what the singularity formation of those fluid equations means for the particle system. So those fluid equations, like compressible Euler, we know in many cases they do develop singularities. Like we have shock singularities, which has been known for a very long time for compressible Euler. There's also recent constructions of implosion singularities at a point. And all those tell you is that the model stops being the right model in some sense. But what does this really mean for the level of the particle system? What is happening for the particle system? For the particle system, Newton's laws do not blow up. So this is a very good thing about Newton's laws. They do not blow up. And this might give a chance, by us really studying this rigorous derivation of the hydrodynamic limit, it might give a chance to understand what is really the right model after the blow-up for those fluid equations, which is a very interesting question. And in some sense, this particle system should pick for you the right extension. Okay, if you think about it in in the class of weak solutions. There are many weak solutions that come after the singularity. There's class of theorems that fluid mechanics or weak strong uniqueness. That after the singularity, you stop having uniqueness. And then the question is whether, like, really a true or a good understanding of this connection between the particle system and the fluid limit allows you to pick back again a unique solution. Something like what happens with entropy solutions for Berger's equations. We pick one that is unique and this physical one. Again, those are all challenges for the future, and no one knows how to do it at this point. And this is it. I'll stop here.
Okay, so questions, comments? So
I mean, you mentioned that you really need hard spheres. I mean, so why is it so difficult to get, a little bit of interaction potential, which is not a hard sphere? I mean, why
you should probably, you can do just like in King's theorem, like you can do interaction potentials that are compactly supported. But the minute you get away from compactly supported potentials, things become much
compactly supported, you think?
Yeah.
Oh, I see.
Yeah.
I think that in that case, you have to take into account the small time in which two particles are overlapping. Yeah, that's annoying, but it's, I don't think that it. But for long range,
No, but I just wonder, I mean, your scheme, I mean, when you can do this derivation for all times, I mean, can you really put also a smooth potential? I mean, even
I think it should be possible. There's a student working on that. But yeah, I think it should be possible.
So the question is.
Boltzmann and many-body Schrödinger equation is, let's say, a very challenging problem. But do you expect it to be more similar to particle systems or to kinetic wave theory?
I think it's more close to kinetic wave theory. Partly because I mean it is really very similar to the kinetic wave theory for the Schrödinger equation. Because if you look at the in the second quantization picture, it's just a non-commutative version of that, where you replace the Fourier modes, which are complex numbers for NLS. They become creation and annihilation operators. And another reason why it's closer to the wave theory is that it is really a weak coupling. And to get the quantum Boltzmann equation, this is a weak coupling limit rather than a Boltzmann grad limit. So, and the same thing goes for the wave kinetic theory. It is also a weak coupling limit. So yes, I think it is much more close to the wave theory than to the particle theory.
Other question? So, if not, let's thank you.